Now if we look at the Carnot cycle on a TS diagram, it will make a lot more sense. Let's go back and review each of the processes on the Carnot cycle, and rather than looking at it on a PV diagram, the TS diagram will be much more, how should we say it, aesthetically appealing or intellectually satisfying. The first process was a constant temperature expansion process. So it wasn't adiabatic because heat was being transferred in. We moved from state 1 to state 2 at constant temperature. So this is an isothermal process. So you notice the upper horizontal process line represents this process, moving from state 1 to state 2, and since heat is flowing in, it should make sense that state 2 is to the right on the entropy diagram. In other words, the entropy of the air in that system has increased, and that should make some sense also because remember, the piston is expanding. So the ways that the energy can be distributed in that system have increased, therefore the entropy or the randomness of that thermal energy has been increased because there's simply more space for the energy to exist. Now, has the amount of energy of the air itself changed? No, it hasn't, because remember, air is an ideal gas, and what we learned from Joule's experiment is that the temperature of the air determines the amount of energy in the air. So the energy has not changed. It's the way that that energy is spread out that has changed. In other words, its entropy has increased in moving from state 1 to state 2, even though the temperature has been constant. So that was the first process, reversible isothermal expansion with heat addition. The next process was to cap off the piston cylinder device, in other words, make it adiabatic, do not allow any heat to flow, and instead allow the piston to continue expanding as the temperature of the gases drop. Now, this is a reversible thing with no heat transfer. If that's the case, then no entropy is being generated, right? So the entropy of the system from state 2 to state 3 is constant, which kind of makes sense because while there is more and more space for the energy to exist and therefore more configurations for the energy to exist in, the temperature is going down, right? There's less energy in the air because its temperature is decreasing from state 2 to state 3. And this should make sense, right? Because if the piston is still doing work, then the gases, let's just say it's air, are losing energy, as exemplified by the fact that the temperature goes from TH to TL. So from state 2 to state 3, we have a reversible adiabatic expansion process where the temperature drops, so it makes sense that we've got a drop from state 2 to state 3 on the vertical axis, but there's no entropy change on the horizontal axis. So as we go to state 3, this is one of those two special cases I showed you before. It's just a vertical line and no heat transfer occurs, which makes sense. So the next process is reversible isothermal compression from state 3 to state 4, the lower horizontal process. Now notice that the area underneath this process curve from state 3 to state 4 represents the amount of heat transfer during that process because this is a reversible process. So it's not just internally reversible, it's totally reversible. So that area bounded by A43B back to A represents the amount of heat transfer out of the system, QL, during the process from state 3 to state 4, the reversible isothermal compression process. Now remember what's happening here physically is that we're putting work into the piston, compressing the gases but at constant temperature. So if the gases remain constant, what that means is that the amount of energy in the, let's say it's air, so it's an ideal gas, the amount of energy remains constant, but the number of ways that the energy can be distributed within that that volume is reducing because we're simply making it smaller, right? And so the entropy of the system is decreasing. And now you see why state 4 or how state 4 is related to state 1. In the PV diagram, it looks just kind of random, right? Like, okay, we better hit state 4 just right so we can curve up at, constant entropy is really what it was, to state 1 and complete the cycle. But now you see that really what we're doing, since this is a reversible isothermal compression process where all of the work that comes in leaves as heat, well then state 4 is simply a state that needs to end back at the entropy that state 1 has, because the next process is to remove the thermal energy sink, insulate it, and finish the compression so that we go to the correct volume where we started at state 1 and the correct temperature TH. And that will happen if state 4 is directly below state 1 on the TS diagram. So this is our final reversible adiabatic compression process. So again, hopefully this clarifies the Carnot cycle and makes some more sense of it. Now the net work, of course, that we get out is equal to the difference in the heat flows just by an energy balance around the process. So it's QH minus QL. So interestingly enough, just like on the PV diagram, the area enclosed by the cycle from state 1 to 2 to 3 to 4, that area still represents the net amount of work done by one cycle on this diagram, just like it did on the PV diagram.